In this lecture, we're going to be talking about one of my favorite things, depositional environments. So what are depositional environments? These are the conditions in which sediment is deposited. And so we have sediment accumulation that occurs in specific locations. And with that, they carry specific features and that tell us the way that they've been deposited. And these can be deposited through different processes like physical, chemical, and biological processes. And when we talk about depositional environments, there's generally three broad categories. First is continental, second is transitional, and third is marine. So here's a diagram of where we see these different environments. Again, so first is continental, and this is where we're typically on land, and we have these types of depositional environments, things like glaciers, streams, lakes, and then we have the marine environments, and this is underwater. So we have deep marine, reefs, submarine fans, and then in between is that transition environment. So these are things like tidal flats, barrier islands, and lagoons. So we're going to be giving examples of these three different categories of depositional environments. So first, continental environments. These are deposited on land. And some of the examples would be braided stream and meandering stream, and those are called fluvial deposits. Things like an alluvial fan or sand dune, those are called desert. And then we have glacial deposits, which are, of course, associated with glaciers. And deposits in each of these environments possess combinations of features and that allow us to distinguish between them. So for example, a braided stream is going to look really different than a sand dune. So when we talk about a fluvial system, remember that means it has to do with rivers and stream activity. And these can accumulate in two different ways. One is a braided stream system and the other is a meandering stream. So the differences between the two. So in a braided stream, you have broad, shallow channels, and you see features like cross-bedding, and typically there is no mud. Now, contrast that with meandering streams, where you have lots of winding channels, you have very fine-grained sediments, you have point bar deposits. You might also see cross-bedded, but it's going to be different geometry. And you have an overlying and erosional surface. And these are some of the features that are different between the two. So let's look at a braided stream. So here's an example. Here's a picture of a braided stream. And you can see that the deposits here are mostly conglomerate. They could be cross-bedded sandstone. And things like finer sediments like mudstones and muds and clays are rare or absent. So if we were to look at a cross-section of a braided stream, we would see these types of features of cross-bedded sandstone. We see some conglomerates, but not a lot of mudstones. Now, if we look at a meandering stream has a lot of mudstones. We see things like point bars, and we don't see a lot of things like conglomerates. And that's because the velocity difference between a meandering stream and a braided stream is different. A meandering stream is very gradual and slow, it meanders. And so it allows for deposition of those really fine sediments. Okay, let's talk about deposition in a desert setting. So in a desert basin, we have things like alluvial fan, sand dunes, and Playa Lake deposits. So windblown dunes are typically composed of well-sorted, well-rounded sand. We have cross beds that can measure in the tens of meters high. And any land-dwelling plants and animals make up any of the fossils. So we wouldn't see any shells or any corals or anything like that. Most of the fossils that we see are land-dwelling. So here's an example here of a Playa Lake deposit in Utah. So you can see where just in the distance here is some sand that doesn't look like it may belong. So in a dune cross-bed, so if we look at an example of cross-bed, we see here that I've outlined roughly where those beds are. And you can see how this is slightly different than the bedding direction above it. And this is where we have deposition and erosion, which changes the direction at which the beds are deposited. And we call this cross-beds. Okay, let's look at alluvial fans and playa lakes. So alluvial fans form along the margins of a desert basin. And this is where we have stream and debris flow discharged from mountains onto a valley floor. And they form a triangular or like a fan-shaped deposit of sand and gravel. So in this top right picture, this is from Death Valley. And if you were to look at a cartoon version of that, you see that there's this channel that feeds sediment down this slope. And as it reaches the valley, it spreads out into a fan, into the alluvial plain. And so if we were to look at this on Google Earth, I'm going to switch windows here. And if we go to Death Valley, you can see here that on the edge of where we are in the Black Mountains of Death Valley, if I zoom in, here's an example of an alluvial fan. And we can rotate a little bit and see the shape of this, how these are mountains, and that there's this this source of deposit here that comes here, and then once it reaches the valley, then it spreads out into this fan. You can see it quite clearly. Okay, let's go back to the PowerPoint. Okay, and the next is a playa lake. So the more central part of a desert basin might be the site of a temporary lake, like a playa lake. And this is where we see laminated mud and evaporites. Okay, next is glacial environments. So all sediments deposited in glacial environments are collectively called drifts. And so where we see deposition as a result of glaciers is specific characteristics, and we call that till. And till is poorly sorted, non-stratified drift associated with the glacier. And these are deposited directly by the glacial ice. And mostly in ridge-like deposits, these are called moraines. So if you've been to the Eastern Sierras, you might have seen some moraine deposits. Outwash is the sand and gravel deposited by the braided streams that are from the melting glaciers. So as you have a lot of ice that's melted, those deposits from that stream are called outwash. And there's also very distinct characteristics of glaciers, and these are scratched into the bedrock. So as a glacier retreats, you see these striations in the rock. So here's a picture of a glacier at Mount Shasta, California. And this is the resulting moraine. This is a picture of those sediments that have been deposited. And of course, if you were to look at where the glacier has retreated, you'd see those striations. So let's go take a look at Mount Shasta. So Mount Shasta is Northern California area. And if we go look at Mount Shasta here, this is a current view of Mount Shasta. And we can see where there used to be a glacier probably running right through here. And if you were to zoom in or spend time looking at any of the deposits here around Mount Shasta, you would see some of that rubble, those moraine deposits. Okay, so let's look at those transitional environments. And this is between on land and in the marine setting. So these processes include both marine and continental. So an example of this is where we have deposition, where a river or stream enters the sea and yields a body of sediment called a delta, with deposits modified for marine processes, especially when waves and tides are taking place. So some of these include deltas, barrier islands and lagoons, tidal flats, and beaches. So again, here's that diagram of where we are in transitional environments. We're moving from continental environments to marine environments. So somewhere in between is where we see these transitional environments. So an example of that is a lake delta. So deltas and lakes consist of top-set beds that contain land fossils. The bottom-set beds may contain marine fossils. So this is where we would see a combination of different fossils within one bed or within one type of deposit. And this forms a vertical sequence of rocks that become coarser grained from the bottom to the top. So at the base, you would have coarse grains, and at the top, you would have these fine grains, and a delta builds outward, so it progrades. These are some of the words that we talked about last lecture. Okay, so in a stream or river-dominated delta, we have long distributary channels, and they extend far seaward. So here's a cartoon-ish picture of the Gulf of Mexico over here, and this is the Mississippi River Delta. You can see how this river delta has created these channels and has basically deposited and created all this landmass. So let's go look at it in Google Earth. Okay, so now I'm looking at the Mississippi River Delta, and this is part of the Gulf of Mexico here. So if we can see how this delta has created this separate landmass, and you see all these little channels that come off of it. So all of this sediment that's flowing down from this river created all these channels and is depositing right here in this delta. Okay, next is wave-dominated deltas. So instead of having a river, we see that waves are actually helping deposit some of these deltas. So this is where we have seaward margin is modified by that wave action. And an example of this is near Cairo. And this is where we have our delta plain outlined here in this green color. And we have these barrier islands that are on the edges of the delta plain. So let's go look at that. And what I really like about this example is you can really tell like where the water is going, because you have very stark contrast between the desert and this delta system. So here's Cairo. And if we zoom in a little bit, you can see that this is the delta. And this is where those barrier islands are formed. And this is formed by wave action. So we would see slightly different depositional environments from a wave action versus a river action. Okay, next is a tide-dominated delta. This is where tidal sand bodies along the direction of tidal flow are deposited. So this is where we have tide goes in and goes out, and so we have a lot of consistent deposition due to tides. And so an example of this is near Bangladesh in the Bay of Bengal. Okay, let's go check that out. You can see that this one looks quite different, actually. And so that's because, again, this is influenced by tide. So you can see how the shelf here, the different colors are associated with how deep it is. And so this is a bit shallower. And of course, the darker blue is much deeper water. So this shelf is likely very gradual in the slope because you have the tides that come in and push out. And so it's creating this very different looking shelf. And this is an example of tide-dominated delta. Okay, next is barrier islands. So on a broad continental margin with abundant sand, long barrier islands lie offshore, separate from the mainland by a lagoon. And barrier islands are common in the Gulf and Atlantic coasts of the United States, as well as other places around the world. And some of the sub-environments of barrier islands include we have beaches, we have dunes, there's an inlet here, So here on the dunes, you would see things like shell fragments. And then, of course, in the marine sediment, we would see some possible fossils and bioturbation. So there's a lot of different environments that are composed of a barrier island in itself. So let's go look at the Virginia Beach. So now we're going to fly back over to North America. And here along Virginia Beach, here's an example of that. So if we look back at the little diagram, here's our inlet, and we have dunes on these barrier islands here. And then inside is the tidal flat. So this is the tidal flat. Here's the inlet. And here is our barrier island. And of course, on the barrier island, we would have things like dunes and little structures here. Oh, so here's an example of a tidal flat. So tidal flats are present where part of the shoreline is covered by seawater at high tide and then exposed at low tide. So we would build or prograde seaward. And so we get a sequence of rocks. And again, this is clues into telling us what type of environment it is. So when we see prograding beds, we have finer sediments at the top, coarser sediments at the bottom. It's in a prograding system. And of course, in a tidal flat environment, we would see things like cross-beds. We would see how those sands have been deposited, and then as the tide changes, they change direction. Okay, so now let's move on to marine environments. So in marine environments, much of the detritus sediments have been eroded from continents, and it's deposited into these marine environments. So an example of that would be continental shelf, the continental slope, continental rise, and then the deep seafloor. And so sediments derived from chemical and organic activity are also deposited in shallow marine environments, and these would be limestone and evaporites. So let's take a look at some of these examples. Oh, first, here's again that diagram. So we already talked about the continental environments. We just talked about the transitional environments, and now we're going to look at the marine environments. A delta marine is a gently sloping area that's adjacent to a continent and is a continental shelf. So here is where we have these detrital marine environments. This is high energy that is periodically stirred up by waves and tidal currents. Sediment is mostly sand because we're, again, in that coastal environment. So we see a lot of what used to be maybe sand dunes in the beach that then gets pushed into the marine environment. Bedding plains are commonly marked by wave-formed ripple marks. So you would see remnants of currents and ripples in the sediment itself. And marine fossils and bioturbation are typically present. So we would expect to see shells and maybe reefs and things like that. That would be an example of marine fossils. And bioturbation is where you have those critters and sea life that dig into the sediment. So maybe like a mussel, or a mussel is the only one that comes to mind, where a mussel sort of digs itself into the sand. That would be an example of bioturbation, where you have these critters that dig into the sediment and they remain there once they become fossilized, basically, within the sediment. So let's talk about slope and rise. So the low energy part of the shelf is mostly mud with marine fossils, and then interfingers with the inner shelf, which is mostly sand. So sediment derived from the continents through submarine canyons create these, crosses the continental shelf and then is funneled into deep water. So these sediments then eventually come to rest on the slope, and continental rise as a series of overlapping submarine fans. So we have a lot of different things going on here. So here's an example of the continental shelf. And as these sediments fall down the continental slope, this is where we see this these overlapping sediments here in this region. So once the sediments pass the outer margin on the shelf and the shelf slope, that's when turbidity currents transport it. So turbidity currents are where we have a lot of that underwelling current from the ocean. Okay, let's look at more detrital marine environments. So the main avenues of sediment transport across the shelf are submarine canyons. So here's, again, we looked at a submarine, or we looked at an alluvial fan on the continental shelf, and it's the same type of thing as what we call a submarine fan. And this is where we have the channel, where we have sand coming down, and then it's deposited on the continental rise or seafloor. And we would see similar type of grading upwards with sediment, where we would have some of the larger, coarser sediment near the mouth of the deposit, and then of course on the edges of the fan would be the finer sediment. Okay, and then in the deep sea, so beyond the continental rise, the seafloor is nearly completely covered by fine-grained deposits. That means there's no sand and gravel, and it's mostly muds and clays. And there's hardly any sediment at all near the mid-ocean ridges. If you remember, that would be because we're near the mid-ocean ridges is where we're near plate boundaries typically. So the main sources of sediment in a deep sea environment are wind-blown dust from continents or oceanic islands, volcanic ash, and shells of microorganisms that dwell in the surface waters of the ocean. So some examples of that are in a carbonate environment. So carbonate rocks are limestone, which is composed of calcite. We also have dolostone, which is composed of dolomite. And most dolostone is some altered version of limestone. And limestone is similar to detrital rock in that it has gravel-sized grains. There can also be some sand-sized grains, but we have microcrystalline carbonate mud called micrite, and the grains are all calcite. So if you were to take a bottle of hydrochloric acid or something, it would fizz due to the presence of calcite. And this is formed in the environment of deposition as opposed to being transported there. So this is something that occurs within that environment instead of having the calcite or these carbonate rocks being transported by waves or rivers or something like that. And we see this typically in a carbonate shelf. This is attached to the continent. And so this is where we'd have a difference of, instead of having a lagoon with a sand dunes and sand barriers, we see this with a carbonate barrier. So this has to do with the presence of limestone and dolostone. And these are typically where we see things like barrier islands with reef systems. And this is where we would see this carbonate shelf. And we would have fossils like fossiliferous micrite, and we would have some of these other reef type rocks and the micrite down here as the shelf dips off into the basin. Okay, let's look at some carbonate subenvironments. So reef rock tends to be structured less and composed of skeletons of corals, mollusks, sponges, and other organisms. And carbonate banks are made up of layers with horizontal beds or cross-bedding, or maybe even wave-formed ripple marks. And lagoons tend to have micrite, marine fossils, and bioturbation. Okay, so here's again that example of bioturbation when I said mollusks, but here's an example of some of these critters that are basically embedded, or they bury themselves into sediment, and then they become these little artifacts within the sediment. So if we look at a rock sample here, and we can zoom in to 5 millimeter zoom here, and then you see this little bug, these little guys here, those are examples of bioturbation. And we can tell about the environments because certain critters or bugs or sea life can only exist in certain environments. And based on the size or where they're located, we can also tell a little bit about how old they are. So looking at thin sections and looking at these samples and little bits of bioturbation can tell us quite a bit about the depositional environment. Okay, so evaporite environments, this is where it consists of rock salts or rock gypsum, and they can be found in things like playa lakes, saline lakes, and the ocean. Evaporites are not nearly as common as sandstone, mud rocks, or limestone, but they can be abundantly localized. So an example of this is in the Mediterranean, where it can be over 2 kilometers thick. There's also a few other locations around the world where you would see evaporites. And these are deposited. High evaporation rates of seawater causes minerals to precipitate from solution. And we would see this in coastal environments, as well as arid regions can also meet the requirements of where we'd see evaporites. And evaporites could form in an environment similar to this with, again, the arid region, even in a coastal environment, and then restricted inflow of normal seawater into a lagoon, or just places that have increased salinity and salt deposition. Okay, so why do we care so much about depositional environments? So part of my background is working in the oil and gas industry, and we have to use these tools to tell us about the past in order to understand where oil and gas resources are. So we need to understand things like where our reservoir rock are, how they're formed, and what those rock properties are. And certain rock properties are important in how they carry oil or hold onto hydrocarbons and how we can produce them. And some of these things include porosity, permeability, saturation, and maturity. So a lot of these words that we're going to cover in a future lecture when we talk about rock properties, when we talk about groundwater properties, and we talk about oil and gas industry. So a lot of these things we're going to be talking about throughout the semester, so don't be too overwhelmed with some of the nomenclature. Okay, so when we look at depositional environments, it's important to try to understand what the coastline looked like in geologic past. So roughly here in the red box is roughly the coastline of California. And the yellow star is roughly where we're located in Ventura County. And this is mostly present day. This is the Pleistocene, and it's pretty recent in terms of geologic time. But if we step back into, what is this? This is the late Miocene. So I'm going to close my face so that you can see all of the things here on the screen. So again, here is the image on the left and the right is the same, except that there's these other outlines here to help us try to figure out where we're located. So again, here's the same polygon of the coastal California, but now we're stepped back a few million years. And so during this time, we have a lot of changes happening with plate tectonics. And this whole area is pretty broken up. We're partially submerged underwater. It's not quite a water environment yet, but we're definitely in a coastal environment. You can see here how the transverse ranges are being rotated as a result of the San Andreas and the plate motion of the Pacific plate. So let's step back further to the middle Miocene. It's about 10 million years ago. And so the area looks a little bit different. We have some rotation of the transverse ranges, and part of the coast here is definitely underwater. A lot of the coast is underwater. And if we step back even further to the early Miocene, about 20 million years ago, you can see that most of the coastline is totally underwater. And this actually looks a little bit like a lagoon system. And so where we are roughly located here, you can see that we're within this lagoon system. And so in this time, in early Miocene, we would expect to see deposits that indicate that we're underwater. We'd see shell fragments, or we'd see other evidence of sea life here. And if we step back even further to the Oligocene, about 30 million years ago, you can see that all the islands are completely submerged underwater. And this is very much like a coastal shelf environment going on. Oh, and then step back even further to 50 million years ago in the Eocene. And this is now more like a deep water environment. So just in the time of 50 million years, where the California coastline is today was totally underwater into like a deep water environment system. So what does this mean into the grand scheme of things? So throughout the semester, we're going to talk about what a stratigraphic column is, and we're going to show examples of that. But in the context of talking about depositional environments, I'll just give you a brief overview. A stratigraphic column represents the different layers that are observed within the subsurface with pertinent information like what we call it, what the descriptions are, how thick it is, what the age is, all of these things, what type of stratigraphy we would see there. All of these things are into a stratigraphic column. And so when we look at trying to date these rocks or trying to understand what the depositional environment was at the time, we would use a stratigraphic column to show us how that has changed over time. So if we look at the early Miocene in the coastal California region, we would see deposits of the Lesby Formation and Point Sol Formation. In the middle Miocene, we'd have the Monterey Formation, which is a marine sediment of porcelaneous and cherty siliceous shale. Above that, we would have the Sisquoc Formation, which is a fine-grained diatomaceous mudstone with siltstone, and we see these sandy interbeds. And above that is mudstones, claystones, and turbidite sands. So if you look at a stratigraphic column in these descriptions, this should match roughly with the depositional environment at the time in which they were. I just showed you that those images. So early Miocene, we see things like marine sediments, more marine sediments. As it gets younger, we see things like clay stones and mudstones and turbidites and silts and gravels. And so we have evidence of marine environments from earlier geologic time and things like continental deposits that are more recent in geologic time. So if we were to step through these different sediments, let's look at the lower Miocene. Again, this would be where we'd be in a not quite a deep marine environment, but definitely partially underwater. We actually have evidence of volcanics here. This is the Tranchean volcanics. This is a series of rhyolitic tuffs, pumice, volcaniclastic sandstones, and siltstones. So in the Santa Barbara Channel, the volcanics are less than 100 feet thick of this tuffaceous zone, and sections of the volcanics are missing due to the truncation of the amberjack high that separates the Santa Maria Basin and the Santa Barbara Basin. Don't worry too much about these details. These are just things that we learn as geologists when we're studying depositional environments and what they mean for the region. So the bread and butter of part of coastal California in the oil and gas industry is the Monterey Formation, which is middle Miocene in age. The Monterey Formation is a primary reservoir for production, and it's an organic-rich complex of siliceous to porcelaneous shale and siltstones and cherts and disseminated chert in limestone and dolomite. And these were deposited in a shallow to deep marine events, followed by deposition, burial, and diagenesis. So again, if you remember when I showed you the diagram of middle Miocene, we were in that shallow to deep marine environment. And if you remember when I talked about the diagenesis, this is where we have areas of higher geothermal gradients and that can alter a rock over time. So in the Monterey Formation, we see 3 different phases due to diagenesis. And I'm going to skip some of this other stuff because it's a little bit irrelevant to the conversation when we talk about depositional environments. But above that is the Santa Margarita, or the Sisquoc Formation, and this has diatomaceous laminated mudstones and bedded dolostones, and there's an unconformity that exists here. But the difference that I wanted to show you is that this rock looks a little bit different than the Monterey Formation, and that has to do with how it was deposited. So in this lecture, we covered what a depositional environment is and the conditions in which sediments can be deposited. We talked about the 3 different broad areas of depositions. We have continental, transitional, and marine. So I know that was a lot to take in for this lecture, so I hope you enjoyed learning about depositional environments.